At first, the North Sea does not look like a place that needs explaining. Its horizon is low. Its coasts are familiar. Ferries cross it, fishing boats work it, and millions of people live close enough to smell salt in the wind. On a calm morning, it can seem less like an ocean than a broad space between countries. But that calm surface hides a physical paradox. The North Sea is dangerous for a reason that sounds almost impossible. Its danger is not that it is deep, it is that it is shallow. Shallow water is not a magic switch that makes every wave larger. The truth is more interesting. Wind must blow with the right strength, direction, and duration. Tides and currents must move beneath the waves. Atmospheric pressure can lift the sea, while wind drives water toward the coast. Near shore, the seabed can slow a wave from below, shorten it, and make it steeper. The shape of the shelf, an estuary, or a narrowing coast can then decide where that moving water goes. Danger is built from several forces arriving together. When those forces align, the horizon changes character. A ship that looked powerful beside a harbor wall becomes a small object moving between dark slopes of water. Spray can erase the distance. Steel rises, falls, and rolls as the surface reorganizes beneath it. Yet even here, spectacle can mislead. One violent crossing cannot describe an entire sea, and one exceptional wave cannot become its normal face. The North Sea is dangerous precisely because the severe moments emerge from a place that is usually busy, useful, and close to home. This is not an empty wilderness. Britain lies to the west. Norway and Denmark frame the north and east. Germany, the Netherlands, Belgium, and France meet its southern approaches. Between them run some of Europe's busiest maritime routes. Fishing grounds overlap with cables, pipelines, platforms, protected areas, and fields of turbines. Much of that activity is invisible from land. A clear horizon may conceal a merchant ship beyond sight, a pipeline on the seabed, a porpoise hunting in turbid water, and a storm system still more than a day away. The sea itself is young. Beneath today's roots are river valleys, wetlands, and ground that once joined Britain to continental Europe. As the last great ice sheets diminished and sea level rose, water advanced across that landscape. The change did not happen in one cinematic instant. Coastlines retreated over generations. Low ground flooded. Former high ground became islands, then banks beneath the surface. The name Doggerland now gathers that changing world into a single word. Its remains remind us that the blue shape on a modern map is only the latest arrangement. Covering the land created more than a shipping route. It created a living engine. Tides mix water across the shelf. Winter storms can return nutrients toward the surface. In spring, increasing light allows microscopic life to multiply. That production moves through zooplankton and small fish, then into seabirds, seals, porpoises, and people. Sandbanks become feeding grounds. Mudflats fill with birds, when the tide withdraws. Cliffs turn into crowded nurseries above the waves. The same shallowness that exposes coasts to moving water also helps connect light, seabed, and food. That connection has a human history as well. On the night of the Great Flood in 1953, storm, tide, and waves pushed the North Sea across low coasts. Defenses failed or were overtopped. Darkness and broken communications slowed warnings. Thousands of people died around the basin. The disaster changed forecasting, coastal engineering, and emergency planning. But it did not make the sea harmless. Barriers can resist water at selected places. They cannot remove the wind, the tide, or the continental shelf that helps organize a surge. Today, another transformation is rising from that same submerged landscape. Turbines are being built over Dogger Bank, where drowned high ground became habitat and then an industrial frontier. The North Sea is now asked to provide food, transport, fossil energy, renewable power, and space for wildlife, while absorbing a warming climate and the pressure of nations around it. How can one sea be nursery, highway, workplace, power station, and threat at the same time? The answer begins by replacing the empty blue patch on the map with the moving system it really is. If careful nature films built from real footage matter to you, subscribe to the channel. We are going to follow this sea from the land beneath it to the storms above it, and every image will have to earn its place. From above, the North Sea appears almost enclosed. Britain forms its western wall. Norway and Denmark shape the long turn to the north and east. Germany, the Netherlands, and Belgium meet its low southern edge, while France stands at the approach to the channel. It looks contained, like water held inside a rough frame of land. But a coastline is not a wall. Water enters, leaves, mixes, and returns. To understand this sea, the first lines on the map must be openings. The word boundary needs care. A physical basin, an ecological region, a forecast area, and a national jurisdiction do not use one outline. Scientists using the Greater North Sea may include the channels between Norway, Denmark, and Sweden, and waters reaching north toward Shetland and Norway. A chart may divide it another way. Every map here will show what its line means. A management edge must not become a wall in the water. The widest exchange lies to the north. Beyond Orkney and Shetland, the shelf opens toward Atlantic and Norwegian waters. A smaller Atlantic route enters from the southwest through the English Channel. Farther east, the channels between Norway, Denmark, and Sweden form the path toward the Baltic. These are not three identical doorways. Their depths, tides, salinity, and flow differ. Together, they make the North Sea less like a closed bowl and more like a busy room with several doors, each opening onto a different body of water. Most Atlantic inflow arrives from the north. Some water passes around and between the northern islands, and some enters along the western side of the Norwegian Trench. On the broadest map, the circulation bends anti-clockwise around the Shelf Sea. Much of the water eventually leaves along the Norwegian side, while the channel contributes a smaller inflow in the south. This is a general pattern, not a conveyor belt fixed to the seabed. Wind, season, and changing Atlantic conditions alter its strength and position. Now remove the current arrows and let depth replace them. The southern North Sea spreads across a shelf commonly less than 50 meters deep. Farther north, the floor falls away through deeper water. Along Norway, the trench cuts a long, dark route that reaches hundreds of meters below the surface. Banks interrupt the shelf, channels cross it, and river mouths open into it. The memorable truth remains that this is a shelf sea, but the honest picture is uneven. Shallow is its dominant character, not its only depth. That uneven floor is not background scenery. It changes how water can move. A broad, shallow area gives tide and wind a different geometry from a deep trench. Banks redirect flow. Narrow approaches concentrate it. Near a coast, friction reaches through a large part of the water column. Over deeper northern water, surface heating can separate a warmer upper layer from colder water below. Bathymetry is therefore part of the machinery. The shape beneath the sea helps decide which forces can reach from surface to seabed. The tide adds another motion. At a beach, it is seen as a rising or falling line, but across the basin, it is a traveling change in water level and current. Flood becomes ebb. Channels accelerate flow. Around headlands and islands, timing shifts from place to place. Water can move strongly in one direction for part of the cycle, then reverse, while the much slower residual circulation continues beneath that repeated movement. A single arrow cannot show both stories. The map must breathe, advance, and turn back. Tide is only one driver. Wind transfers momentum into the surface. Rivers add fresher water along the coast. Differences in salinity and temperature change density. Pressure gradients tilt the sea by amounts too small to see from a ship, yet large enough to help move water across a basin. These forces overlap rather than taking turns. The current beneath one quiet horizon is the combined result of motions measured in hours, seasons, and years. This is why a fixed map can explain a pattern but never capture every moment. At the eastern gateway, water heading toward and from the Baltic carries another signature. The channels between Norway, Denmark and Sweden are less saline and less tidal than much of the wider ecoregion. Their water column is often layered. In the southern North Sea, large rivers and shallow energetic water create a different balance. Atlantic water still reaches this region from north and southwest, but it mixes with fresh water arriving from the surrounding land. The sea between nations is also a meeting place between catchments. Mixing changes with geography. Across much of the shallow south and east, tides and wind keep the water column stirred through the year. Surface and seabed remain closely connected. In much of the deeper north, summer heating can create seasonal stratification, with lighter warm water above denser cold water. The division is not a straight border. Fronts move, storms break layers, and local depth matters. Even so, the contrast is fundamental. One sea can be vertically connected in one region and seasonally divided in another. Season changes the map again. Winter winds cool and stir the sea. Summer sunlight warms the surface, especially where the water is deep enough for tidal mixing to weaken before it reaches the top. A storm can disturb a layer that took weeks to form. A persistent inflow can bring different temperature and salinity into the north. None of this makes the broad circulation meaningless. It makes it alive. The arrows are a long-term summary of water that is always responding to weather and exchange beyond the frame. Then, the human layers appear. In the north, fishing grounds share water with oil and gas infrastructure. In the shallow south, ships converge on ports while fishing, gas production, wind farms and sand extraction occupy the same regional map. Cables and pipelines cross boundaries that currents ignore. Protected areas add another geometry, drawn for habitats and species whose movement may extend beyond them. The result is not one crowded surface. It is a stack of activities above, within, and beneath the water. A merchant ship sees only part of that stack. From its bridge, the sea may look empty, except for another hull on the horizon. The chart shows routes, separation schemes, depths, hazards, and approaches to ports. Below the keel may lie a cable carrying electricity or data. Farther away, a trawler may be working beyond sight. The open view is real, but so is the hidden organization. Emptiness on the horizon is often a failure of scale. The same is true from land. A beach in Norfolk, Jutland, or the Netherlands offers a narrow slice of a basin extending far beyond sight. The water at that edge has been shaped by tide, wind, river flow, and exchange with the Atlantic. Wildlife moves through it. Commerce moves across it. Weather reorganizes it. Each coast experiences a local North Sea, yet none is separate from the whole. The sea connects places whose view of it can be entirely different. But the last sentence hides a surprise. This basin has not always existed in its present form. The routes on the modern map cross a floor cut by older rivers. The bank beneath turbines and fishing vessels was once part of a wider landscape. If the blue water layer is removed, the borders between nations lose their familiar shape. Britain moves closer to continental Europe. Channels become valleys. The North Sea stops being a permanent fact and becomes a recent chapter. The floor beneath the shipping lanes was not always a floor. Its sand preserves the evidence of a drowned world. The survey camera descends into green water and finds a plain of sand. Nothing in the image announces a lost country. There are no walls, roads, or roof lines. A shell moves past the lens. Fine sediment lifts, settles, and hides the marks just made above it. Yet this seabed sits inside a landscape archive. Beneath the moving surface are older layers, cut by rivers, altered by ice, covered by wetlands, and finally reached by the sea. The first task is to separate what the camera sees from what the sediments remember. The present seabed is not simply an ancient land surface with water placed on top. Waves and tidal currents have reworked its upper sediments for thousands of years. Some older surfaces were buried beneath younger sand. Others were eroded. Modern bathymetry shows the floor that exists now, not a perfect map of any single moment in prehistory. To look backward, researchers must work through that disturbance. The lost landscape is not waiting intact like a room behind a door. It has to be reconstructed from surviving pieces. Those pieces reach far beyond the period usually associated with Doggerland. Across repeated cold stages, ice sheets expanded and sea level fell. During warmer intervals, water returned. Rivers changed course. Glaciers cut, carried and deposited material across the basin. For parts of this long history, ground now beneath the southern North Sea was available to animals and several human populations. The region was not merely a bridge crossed on the way somewhere else. At different times, it contained rivers, plains, wetlands, and places worth inhabiting. Doggerland is the modern name given to part of that changing world. It is useful because it turns empty blue space back into land, but the word can also mislead. Doggerland was not one island with a permanent coastline. Its extent, climate, and habitats changed. In one period, broad ground joined Britain to continental Europe. Later, rising water divided the landscape into peninsulas, wetlands, estuaries, and islands. A map that is accurate for one date may be wrong for another date only a few centuries away. At the end of the last ice age, warming reduced the great stores of land ice and global sea level rose. Water advanced across low ground in stages. It entered from the north and through the channel system in the southwest. River valleys became estuaries. marshes moved inland. Former interior ground approached a coast that had not existed before. This was not one cinematic wall of water. For much of the landscape, inundation was a long transformation measured across generations, interrupted by faster episodes and local events. Evidence sometimes arrives without a map. Fishing gear and aggregate dredging have brought bones, antler, and stone from the North Sea floor. Collections include animal remains, tools, and fragments of human bone from different places and periods. A hand axe can prove that a person shaped stone somewhere in the wider landscape. It cannot, by itself, reveal the route that person walked or the exact surface where the object was left. Recovery gives archaeology an object while often taking away the context that would explain it. Lost context is why a dramatic find needs care. A bone lifted by a trawl may no longer sit in its original layer. Dredging can move material before anyone recognizes an artifact. Dating, species identification, wear, cut marks, and chemistry can recover parts of its history. But an isolated object is not permission to invent a village around it. The strongest reconstruction begins with what is known and keeps the uncertainty visible. Other evidence never leaves the seabed as an object. Acoustic and seismic surveys send energy through the floor and measure the returning signal. Processed in 3 dimensions, those reflections can reveal buried structures, former drainage systems, lake features and salt marshes beneath later sediment. The result is powerful, but it is not a photograph of a vanished river. It is data interpreted through geology, geometry, and time. Field samples, independent dates, and careful validation are needed before a bright line in a survey becomes a feature on a paleogeographic map. Cores provide another kind of vertical journey. A tube of sediment preserves layers that may contain pollen, plant fragments, microscopic remains, and changes in grain size or chemistry. Read together, they can suggest whether an environment was marine, freshwater, marsh, forest, or open ground. Radiocarbon and other dating methods place some of those changes in time. No single core describes the whole basin. Each is a narrow sample. The landscape emerges when many samples are connected to seismic structure, sea level history, and modern position. People lived within this changing region, but direct knowledge of their lives is limited. Evidence from neighboring lands can suggest technologies, diets, and ways of moving through comparable environments. Simulations can test different behaviors against a reconstructed landscape. Those behaviors remain hypotheses. A figure hunting beside a digital river is not an eyewitness account. It is one possible answer built from evidence and analogy. The distinction matters because the people of Doggerland are often shown with more visual certainty than the ground beneath them deserves. What can be said safely is still extraordinary. Families could have known coastlines that shifted during a lifetime. Places used by one generation may have become tidal ground for another. Rivers linked freshwater, wetland, and coast. Rising water did not simply remove land, it changed routes, resources, and the meaning of distance. Yet the rate and experience differed by place and period. There was no single last morning when everyone looked east and saw the same world disappear. The archaeological record does not give us that scene. Then, around 8,150 years before present, a different kind of event crossed the region. A vast submarine landslide off Norway generated the resulting tsunami. Evidence of the wave exists around northern European coasts and within southern North Sea sediments. For communities in exposed low ground, the arrival could have been devastating. But even a real catastrophe can gather a simpler story after thousands of years. That tsunami is often described as the wave that ended Doggerland. The evidence does not support so clean an ending. Topography changed the impact. Some channels and low areas could focus water. Other ground may have been partly sheltered by the remaining bank or island. Research from the southern North Sea indicates that floodwater withdrew and parts of the landscape recovered, at least temporarily. The tsunami was neither harmless nor universal. It also was not the permanent final flooding of every surviving remnant. Long-term sea level rise continued the transformation after the wave. A sudden disaster belongs in the story, but it cannot replace the slower process around it. Eventually, former high ground became banks beneath the surface. Dogger Bank preserves the name of that relationship, although its modern sandy seabed has been reworked and does not expose one untouched prehistoric horizon. Above it, ships now pass. Below them, survey instruments trace sediment and structure. The same place can be geological feature, archaeological archive, protected habitat, fishing ground, and energy site. Time has not removed the landscape. It has changed the form in which the landscape can be read. Modern activity creates a final contradiction. Seismic surveys, construction studies, and aggregate monitoring can reveal buried features that might otherwise remain unknown. The activity that produces information can also disturb, extract, or cover the context being studied. Cables, pipelines, foundations, dredging, and bottom contact all meet a seabed with both natural and cultural history. Protection begins by recognizing that an apparently blank patch of sand may contain evidence at several depths. What lies beneath has value, even when it cannot be made cinematic. The young sea inherited the shape of drowned land, and that shape still controls moving water. A valley can become a channel. A rise can become a bank. A shelf can let wind and pressure move water across an immense area. Doggerland explains how the North Sea arrived. It also points toward what the North Sea can do. Once water covered this uneven floor, every storm began working with the landscape below it. A storm begins by changing texture. Wind catches the calm surface and raises short ripples. Those ripples give the moving air more surface to press against, and energy begins passing from atmosphere to water. With time, the field becomes uneven and white crests appear. The waves are not being pushed forward as solid walls. Energy is traveling through a surface made of many different waves, each with its own direction, length, and speed. What looks like chaos from a deck has an evolving structure. Waves still under their local wind are called wind sea. Waves that have traveled away from the weather that formed them are swell. The two can occupy the same water. A storm may therefore build new, short waves across an older system arriving from somewhere else. Their crests can cross at an angle, disappear into one another, and form again. A single height cannot describe all of this. Modern forecasts represent a spectrum of wave energy spread across frequencies and directions. Wind speed matters, but it is not enough. Duration matters because a young sea has not had long to grow. Fetch matters because wind can only work on water across the distance available in its direction of travel. In an enclosed shelf sea, a change in wind direction changes that distance. A gale blowing along the basin can organize a different sea from one blowing toward the nearest shore. This is why the North Sea does not need an ocean-wide horizon to become dangerous. It needs the right wind over the right reach of water for long enough. Even then, there is no one representative wave. Mariners and forecasters often use significant wave height, a statistical description close to the average height of the highest third of waves. Individual waves rise above and fall below it. Period and direction matter alongside height. A steep short sea can punish a vessel differently from a longer swell of similar height. The useful question is not simply how tall the water looks. It is what collection of waves is moving through this place, and what will it meet next? Beneath the waves, a storm can move the mean level of the sea. This is the surge. Strong wind drives surface water toward a coast and allows it to accumulate. Low atmospheric pressure makes a smaller contribution by raising the level beneath the storm. The Met Office gives a useful rule of scale, roughly 1 centimeter for each millibar of pressure fall. Neither effect is a breaking wave. A surge is the broad platform of elevated water on which the storm's waves continue to run. Direction decides where that platform develops. Wind blowing away from a coast can lower water there. Wind aimed toward land can raise it. The size and track of the storm matter, as do the shape of the coastline and the seabed. The same weather system does not produce one uniform water level around the basin. A bay, estuary, or narrowing reach can experience a different outcome from an exposed coast nearby. Surge is therefore a map of local consequences built from a basin-wide event. Then, the astronomical tide enters the calculation. Tide would rise and fall without the storm, driven on its own schedule. Surge adds a weather-driven departure from that predicted level. If the largest departure arrives near high water, the combined level can become far more dangerous. If it arrives a few hours earlier or later, the coast may be spared the same peak. The waves above are still a third layer. They can strike, run up and overtop a defense, even when the broader water level stops below its crest. Closer to land, depth starts to transform the wave field. The seabed influences propagation. Waves can shoal, bend as depths change, interact with currents, and eventually break because the water is too shallow to carry their former shape. None of this means that shallower water simply makes every wave taller. Some energy is redirected. Some is dissipated. Local contours decide where a wave shortens, steepens, turns, or breaks. The dangerous pattern belongs to a particular coast at a particular water level. Current adds motion beneath that pattern. When waves meet a tidal stream, their wavelength, steepness, and direction can change. Long observations from the Pheno 1 platform in the southern North Sea show that both following and opposing tidal currents alter wave statistics, with opposing flow producing the larger increase in steepness in that dataset. This is a correction to a simple slogan, not a new one. An opposing tide does not guarantee a rogue wave. It changes the field of possibilities that a forecast must resolve. The coast receives all these processes together. Offshore wave generation, tide and surge become nearshore shoaling, refraction, current interaction, and breaking. At a beach or seawall, the result becomes run-up, overtopping, overflow, or, in the worst case, a breach. Engineers separate the stages because each needs a different model. The water does not separate them. A family behind a defense experiences only the final depth and speed of the flood. This is why the opening proposition needs precision. The continental shelf helps wind, tide, and pressure communicate with the seabed and the coast. It does not act alone. A severe North Sea event is a sequence of alignments, a storm track, a wind direction, enough time and fetch, an astronomical tide, a local current, a particular depth profile, and people or structures in the receiving place. Remove one part and the outcome may change. Rearrange their timing and it may change again. Forecasting begins by measuring this moving system. Weather observations and atmospheric forecasts describe the storm. Tide predictions provide the astronomical rhythm. Surge and wave models estimate the departures and the sea state. Buoys, gauges, and other observations test the result. The output is not one prophecy. It is a changing set of expected levels, wave conditions, timings, and uncertainties, translated into local impacts by forecasting agencies. Every extra hour matters only if the warning can reach someone who knows what to do. Far offshore, measurement once changed what engineers were prepared to believe. On the first day of 1995, severe weather crossed the northern North Sea. At 3 in the afternoon, Coordinated Universal Time, a downward-looking laser on a Norwegian offshore gas platform recorded the surface beneath it. The instrument was not filming a wall of water. It was measuring distance through time. In that line, one crest rose far beyond the surrounding record. The measured wave was 25.6 meters from trough to crest. Its crest reached 18.5 meters above the undisturbed surface. The significant wave height around the platform was estimated at almost 12 meters. Those numbers describe different things, and their difference is the point. The sea was already severe, but one wave stood exceptionally high within it. The record gave instrument evidence to reports that had often arrived as stories from ships, and it forced extreme loads to be treated as more than sailors' folklore. That exceptional measurement must not become the everyday North Sea. It was an exceptional observation inside a large storm, not a standard winter wave and not a measure of the whole basin. Nor should a dramatic clip from another place be allowed to impersonate it. The honest image is the measurement itself, a line, a time, a platform, and a scale. Real storm footage can show the surrounding kind of weather. It cannot be labeled as the recorded crest. Later, high-resolution hindcasts examined the weather and wave field around the platform. The European Centre for Medium-Range Weather Forecasts found a fast, southward-moving polar low and a substantial local wind-generated sea. Its analysis also indicated partly crossing wave systems near the platform. The researchers described conditions that may have made an unusually high crest more likely. They do not reduce the event to one cinematic cause. Resolution matters here. A model coarse enough to smooth away the small low also smooths away part of the explanation. The record did not reveal a sea governed by monsters. It revealed a probability that design and forecasting had to respect. A wave field contains variation. Storm structure, crossing systems, non-linear exchange, and current can change the tail of that variation. Most waves remain closer to the surrounding state. Rare ones do not. The lesson is quieter than the legend and more useful. Exceptional water can emerge from measurable conditions without arriving on schedule for a camera. Offshore, the question is whether a hull, platform, or working crew can survive the next load. At the coast, it is whether elevated water and waves will pass a dune, dike, or wall. The physics connects those places, but vulnerability gives the event its human scale. A perfect forecast cannot lower the tide. A defense cannot calm the wind. safety depends on measurement, design, communication, and action arriving before the water does. At the end of January 1953, those protections were not yet the system they are now. A deepening storm moved from waters south of Iceland towards Scotland and the North Sea. Northerly winds began driving water down the long western side of the basin. The tide continued toward high water. Telephone lines and warning chains waited on land. The mechanisms were no longer separate lessons. They were converging on low coasts in darkness. The boundary began moving on the night of 31 January 1953. Along several North Sea coasts, people went to bed behind dunes, sea walls, and dikes that had made water seem contained. Beyond them, a spring tide was rising under a severe northerly storm. The surge beneath the waves traveled faster than news of its consequences. In darkness, the familiar line between field and channel, road and shore, became a route for the sea. On low land, a small rise in water level could move the shoreline farther than any offshore photograph would suggest. The storm had developed south of Iceland and deepened as it moved east. By midday on 31 January, its center lay over the North Sea between Aberdeenshire and southern Norway. Force 10 and 11 winds blew from the north over western parts of the basin. The Met Office account describes waves above 8 meters and water driven south. The surge formed off northeast Scotland, ran down the coasts of Scotland and England, then continued toward the Netherlands. By about 4 in the morning on 1 February, it had reached IJmuiden on the Dutch coast. This was not the tide alone, and it was not a single wave. Low pressure and sustained wind raised the water level. The storm field directed that water along the basin. High spring tide placed an already elevated astronomical level underneath it, while large waves attacked the edge above. On the Dutch coast, a northwesterly force 10 storm arrived on Saturday evening. Each coast met the same connected event through different depths, defenses, and times. The weather and surge had been forecast, but a forecast is not yet a warning received. In 1953, there was no national public flood warning system in England. Wind brought down telephone lines in Lincolnshire and Norfolk, and the Met Office records that almost no warning of the storm's severity passed to counties farther south before it was too late. People beyond the first floods could not see the surge approaching. Many slept while the evidence was already arriving up the coast. A correct forecast held inside an office could not protect a coast that never received a clear instruction. The English toll must keep its own boundary. The Environment Agency records 307 people killed in England. It records 24,500 homes damaged or destroyed, and more than 30,000 people evacuated. Those are national figures, not a total for Europe, and not a count of deaths at sea. They describe disaster spread from Yorkshire to Kent, but the scale was never only a number. Every entry belonged to a street, a family, and a place where water had crossed a defense. Official chronology gives the night local names. By midnight, Felixstowe, Harwich, and Malden were flooded. Soon afterward, sea walls on Canvey Island failed, and 58 people died there. At Jaywick, the Met Office says the sea rose by a meter in 15 minutes, and 35 people drowned. These details should not be arranged as escalating spectacle. They show how little time remained once water found a path across flat ground. Survival depended on decisions made without a complete picture. People climbed to upper floors and roofs. Neighbors, emergency workers, and boat crews entered flooded streets. Some routes vanished under dark water, while debris and broken defenses changed the current. Rescue was improvised from whatever remained usable: a staircase, a roof, a small boat, a neighbor who knew the ground. The most honest archive does not treat the flooded landscape as scenery. It follows the people enduring it, and it leaves room for what a silent image cannot tell us about cold, fear, and loss. Across the water, the Dutch disaster followed its own sequence. Rijkswaterstaat records that the storm reached the coast on Saturday evening. Dikes in Zeeland, South Holland, and North Brabant failed at more than 150 places. A second high water period on Sunday afternoon caused more deaths than the first. This was not one break releasing one flood. Many breaches opened across islands and low polders, and water entered from several directions. Rijkswaterstaat gives the Dutch human toll as 1,836 lives. It records 72,000 people evacuated and more than 150,000 hectares inundated. Thousands of animals died, homes and buildings were destroyed, and salt water spread across farmland and infrastructure. These figures belong specifically to the Netherlands. Keeping that scope visible is not administrative tidiness. It prevents different national tragedies from being blended into a single dramatic total that no source actually defines. Other losses require their own lines. Official British accounts record 19 deaths in Scotland. An Environment Agency account separately records more than 177 lives lost at sea during the East Coast surge, apart from the 307 lost on land in England. These figures should not be casually added to a rounded European total. They were compiled across different jurisdictions and categories. The careful statement is also the true one. Thousands of people died around the North Sea and at sea during the disaster. By daylight, the water had redrawn whole districts. Roads ended in open flood. Fields became temporary sea. Dikes and embankments appeared as broken lines between broad sheets of water. But even aerial scale can hide the duration of the aftermath. Evacuation, shelter, recovery of the dead, repair of homes, and the removal of salt from land continued after the tide withdrew. Maps show maximum extent. They do not show the repeated work of making flooded places habitable again. The event was one night on a weather chart and a much longer period in the lives of communities. The flood exposed more than weak structures. It exposed a broken chain between forecast, warning, and action. A prediction made at national scale had to become a message for a particular coast, then reach people in time, then prompt a workable response. Modern flood systems treat those links as one operational problem. Observations, tide predictions, and weather forecasts feed surge and wave models. Agencies then translate physical conditions into expected local impacts and warnings. England invested in stronger sea defences and more effective warning systems after 1953. The Thames Barrier became the most visible structure, but the wider change includes barriers, embankments, gates, monitoring, and plans along many coasts. The purpose is not to stop the North Sea from moving. It is to manage the routes by which extreme water can reach people. Every defense has a design range, an operating rule, and land that remains behind it. A defense is also a chain of maintenance, forecasts, operators, and decisions that must still work in a storm. In the Netherlands, the catastrophe drove the construction of the Delta Works. Barriers and strengthened dikes changed the relationship between the southwest delta and the sea. Rijkswaterstaat also describes protection as unfinished work. Dikes are raised or reinforced. Barriers are managed. Room is made for high water, and warnings are issued early. The lesson is not that engineering defeated the flood. It is that safety became a continuing national practice shaped by the memory of failure. December 2013 tested that changed system. The North Sea produced another major surge, with some places recording their highest tides since 1953. The Met Office says the possibility was identified to emergency responders more than 5 days ahead, with greater certainty 3 days ahead. Gates were closed, services prepared, and warnings issued. Flooding and damage still occurred. The Environment Agency records no deaths from that flooding. Better preparation changed the human outcome without cancelling the event. That contrast can become dangerous if it sounds like an ending. Surges still occur. Defenses can be overtopped, outflanked, or exceeded. Forecasts carry uncertainty, communications can fail, and rising sea level changes the starting height beneath future storms. A barrier protects selected ground. It cannot protect every coastline or remove every consequence. Maintenance and rehearsal are part of the defense. The achievement since 1953 is not permanent immunity. It is more time, more information, and more layers between an extreme sea and a sleeping community. The flood is remembered at the edge of the basin, where loss was visible. Its physical story began farther out, across a shelf that channeled wind-driven water southward. One rise on that shelf barely appears from the surface. It did not cause the 1953 disaster, and no single bank can explain a basin-wide surge. But Dogger Bank belongs to the same underlying geography. It is drowned ground-shaping habitat, current and human use beneath an ordinary-looking horizon. Far from the dikes, the seabed rises so gradually that a camera cannot reveal the summit. To see Dogger Bank, the film must descend into scientific footage and learn how to read sand. The camera enters green water and settles above sand. Its lights illuminate only a small, moving patch. Grains pass beneath the frame. Shell fragments appear, then fade into suspended sediment. There is no cliff and no moment when the vehicle crosses a visible summit. Dogger Bank is a broad rise, not a mountain hidden underwater. Its scale lives in bathymetry and survey position. Depth changes too slowly for a narrow lens to provide scale. The camera can show what covers the bank, but not the full shape of the bank itself. This is not generic seabed footage. It belongs to a British marine science survey carried out from the research vessel Endeavour in April 2008. During a 19-day cruise, teams used acoustic instruments and ground truthing methods, including grabs, trawls, and underwater video. The separate measurements mattered. Sonar could map form across distance. Samples could reveal sediment and animals. Video could place visible surface features in context. No one method was asked to describe the whole habitat. The name Dogger Bank is used at more than one scale. The geological and bathymetric bank extends beyond United Kingdom waters into Dutch and German waters. Inside that wider feature sits the United Kingdom Dogger Bank Special Area of Conservation. A protected boundary is therefore not the outer edge of the landform. It is a legal and management area drawn around a qualifying sandbank habitat. A point can lie inside both shapes, yet answer two different geographical questions. The map must show both outlines, because changing one into the other would change the meaning of every claim that follows. The United Kingdom protected site covers 12,331 square kilometers. The Joint Nature Conservation Committee gives its depth range as 13 to 58 meters below sea level. Those figures describe the site, not every part of the wider bank. Much of the southern bank is particularly shallow, with a large area seldom deeper than 20 meters below chart datum. Across such a vast area, a difference of a few meters can shift wave exposure, sediment movement, and the communities able to persist. Even the relief is restrained. Survey analysis describes an essentially flat central surface, gently sloping across much of its extent, with steeper ground toward the south. At the surface, a vessel may pass above without any visual sign that the floor has risen. The bank becomes legible only when soundings are joined into contours. This subtlety is part of its power. A feature does not need a dramatic face to organize water, sediment, and habitat across thousands of square kilometers. Its core was built through glacial processes. The Joint Nature Conservation Committee's geological work describes material from the last northern European glaciation deposited in a proglacial lake, later overlain by Holocene sands and recent sand waves. Rising sea levels submerged the feature. Tides and storms then redistributed younger sediment across it. The modern bank is therefore neither a surviving hill left untouched nor a simple heap of loose sand. It is an inherited glacial form with an active surface continually reworked by the sea above. Across much of the protected feature, that surface is moderately mobile, clean sand. The Joint Nature Conservation Committee describes the shallower bank as non-vegetated because it is exposed to waves. A mobile veneer of mainly land-derived grains with a smaller biological component lies above older deposits. Gravel appears in patches, often in slight depressions. A frame that looks uniform may therefore cross boundaries too fine for a viewer to notice. Loose sand, shell material, firmer sediment, or a pocket of coarser ground. Many residents are easier to find in a sample than on a screen. Polychaete worms, shrimp-like amphipods, and small clams live within the sand. Hermit crabs, flatfish, and starfish can live on its surface. Much of the living community is literally below the picture. These are site-level descriptions from the Joint Nature Conservation Committee, not permission to name every shape in the survey video. An animal partly buried in low-resolution footage may be visible without being identifiable. The honest caption can remain at the level the evidence allows. Sandbank communities also change across the site. Mobile crest sediments tend to support animals able to bury quickly. Deeper areas sheltered from some wave or current action can hold more burrowing species and attached life on stones or dead shells. Formal advice identifies several broad biological communities distributed across the bank rather than one standard dogger assemblage. The empty-looking floor is a mosaic whose differences may be chemical, buried, or smaller than the camera can resolve. Survey design turns that hidden mosaic into evidence. Acoustic data map texture and form. A grab takes a small volume of sediment and the animals within it. Underwater video records a narrow path across the surface. Scientists compare stations, group similar assemblages, and test how the patterns relate to depth and sediment. The habitat map is an inference assembled from their agreement and their disagreements over time. Each result has a scale. A grab cannot stand for the whole bank, and a 15-minute tow cannot diagnose the condition of a 12,000 square kilometer site. The same caution applies to disturbance. The Joint Nature Conservation Committee states that bottom trawling is likely to have affected bank fauna, potentially reducing long-lived or fragile organisms and favoring robust, short-lived invertebrates. The wording contains uncertainty because ecological condition is inferred from many kinds of evidence. A furrow in one video may invite a conclusion it cannot support alone. Pressure, response, and recovery must be assessed across space and time, not declared from a convenient frame. Protection does not turn the seabed into a museum display. It sets conservation objectives for a living, changing habitat used by people as well as wildlife. Natural waves and currents keep moving sediment. Animals recruit, grow, and disappear. A protected feature can remain dynamic. Conservation is not a demand that every grain stay where it is. Fishing management addresses particular pressures while monitoring tests whether the feature's extent, structure, function, and communities can be maintained or restored. The map is a tool for decisions. It is not a fence beneath the water. On the sides of the bank, sand eels gather another kind of value. The Joint Nature Conservation Committee records them along the bank's edges and western side. They link plankton production to cod, seabirds, and cetaceans, including harbor porpoise. The survey camera may occasionally record a slender fish, but identity still requires station evidence. The ecological claim does not depend on pretending every silver movement is a sand eel. It depends on samples, fisheries studies, and repeated observation across the bank. The Dogger Bank protected site overlaps another boundary, the Southern North Sea Special Area of Conservation, identified for harbor porpoise. That overlap does not mean porpoises remain above the bank or that every sighting is caused by it. It means habitat, process, and prey in the shared area matter within a wider protection network. A porpoise is mobile. The sand bank is fixed. Conservation has to connect those different scales without turning either boundary into a cage. The Joint Nature Conservation Committee's earlier site assessment also records common and gray seals in the Dogger Bank area from satellite telemetry. Neither seal is the qualifying feature of the Dogger Bank Special Area of Conservation, just as harbor porpoise is protected through the overlapping site rather than the sandbank designation itself. These distinctions can look bureaucratic until the question changes. One boundary protects habitat, another addresses a mobile species. The same water can carry both responsibilities. Seen this way, bare sand is not the absence of nature. It is habitat in motion, shaped by grain size, depth, exposure, and the lives hidden within it. It supports prey, receives material from the water above, and returns energy to fish and other predators. The bank's importance is not proved by making every frame crowded. It is proved by connecting the quiet frame to measurements gathered across the wider system. Particles drift through the camera lights like a faint weather system. Some are mineral grains lifted from the bed. Some are fragments of life. Above the bank, tides, seasons, and sunlight organize a much larger exchange that the seabed camera cannot see. To understand why this sand can support worms, fish, birds, and porpoises, the film must now rise from the floor and follow energy to its smallest beginning. On 15 June 2023, a satellite passed over a rare opening in the cloud between Scotland and Norway. Its instrument recorded turquoise structures turning through the North Sea. The image is real, but it is not the view a person would have from a ship. It is a natural color observation assembled from measured light. From orbit, organisms far smaller than a grain of sand had altered the appearance of an immense area of water. The name phytoplankton gathers many kinds of drifting photosynthetic life into one useful category. It does not name a single species, and plankton are not all plants. Some are algae. Some belong to lineages very different from land plants. What joins the phytoplankton is their ability to use light and dissolved materials to build new organic matter. In the open water, that quiet act is the first capture of energy on which much of the food web depends. Light alone is not enough. Growth also requires nutrients in forms the organisms can use. During winter, wind and cooling stir much of the water column. That mixing can return nutrients from deeper water, but it also carries cells through darkness below the well-lit surface. As the days lengthen, the balance changes. When enough light is available for long enough and the upper water becomes less deeply mixed, production can begin to outrun loss. A spring bloom is a process, not a date on a calendar. The process does not unfold in the same way across the whole sea. Much of the shallow south and east remains strongly mixed through the year. In deeper northern water, summer heating commonly builds a lighter upper layer above colder water below. Between those broad regimes are shifting boundaries shaped by depth, tide, weather, and freshwater. The North Sea therefore has no single bloom season that can be applied equally to every coast, bank, and offshore station. Stratification offers an advantage and creates a limit. It can hold phytoplankton in a bright surface layer instead of mixing them repeatedly into deeper darkness. Yet that same density boundary can separate the upper layer from nutrients below. In a persistently mixed region, nutrients may be replenished more readily, while suspended sediment and deep stirring reduce the light available. Productivity emerges from a compromise between illumination and supply. Tide complicates the compromise. Model experiments for the North Sea show that stronger tidal mixing can promote production by easing nutrient depletion in one place, while hindering it elsewhere by lifting suspended material and worsening the light environment. Around Dogger Bank, the transition between mixed and stratified water can redirect where production is concentrated. A front is not a permanent green line. It is a moving physical arrangement whose biological effect changes with local conditions. This is why the satellite image must be read carefully. A sensor measures light returning from the surface and near surface water. Clouds hide parts of the scene. Sediment and dissolved material can alter color. In the June 2023 observation, the milky turquoise suggested that coccolithophores were abundant, but water samples would be needed to confirm the community. The image reveals extent and pattern. It does not replace a microscope or a sample bottle. Under magnification, the convenient word bloom breaks into difference. The United States Space Agency describes diatoms with silica shells and coccolithophores with calcium carbonate coverings. Their pigments and structures can change how surface water appears. Other phytoplankton differ again. These names describe profoundly different organisms. They must not be illustrated by an unidentified swirl from a laboratory reel. The closer the camera comes, the more exact the evidence must become. Around them drifts another varied community. Zooplankton include animals that spend their entire lives in the plankton and the temporary drifting stages of organisms that later live on or in the seabed. Copepods graze, hunt, and are hunted. Fish eggs and larvae share the moving water at particular seasons. A plankton sample is therefore not dust suspended in the sea. It is a crowded set of lives at different scales and different stages. Energy does not climb through this community in one straight ladder. A grazer may consume several kinds of phytoplankton. A larval fish may eat small zooplankton and later change diet. Gelatinous predators take their share. Microbes recover dissolved and dead material. The food web is a network of transfers, detours, and losses. Its efficiency depends not only on how much life is present, but on its size, timing, composition, and accessibility to the next consumer. Some production moves down. Cells aggregate, animals produce waste, and bodies die. A fraction is consumed while sinking. A fraction reaches the seabed, where bacteria and animals process it again. At the same time, larvae of bottom-living animals rise into the plankton before returning to the floor. This exchange is called pelagic benthic coupling. It means that the green water above Dogger Bank and the sand, seen by a survey camera, are parts of one system, even when no single shot can show the connection. The return path matters as well. Organic material is broken down and nutrients are regenerated. Tidal currents can resuspend material from shallow bottoms. In some places, that helps restore nutrients to illuminated water. In others, it increases turbidity and removes light. The seabed is not merely a tray catching what falls from above. It stores, transforms, and sometimes returns material, while animals in and on the sediment redirect it through their own feeding. Nutrients also arrive from land and air. They are essential to production, but more is not always better. Excess nitrogen and phosphorus can drive eutrophication, including elevated algal biomass and oxygen loss when organic material decomposes. Monitoring under the Northeast Atlantic Marine Convention found that nitrogen and phosphorus inputs to the Greater North Sea declined between 1990 and 2019. That is real progress. It is not evidence that every problem has disappeared. The remaining pattern is regional. The latest, the Northeast Atlantic Marine Convention assessment, found improvement over successive assessment periods, while eutrophication persisted mainly in river plumes and some coastal areas. A discolored estuary cannot represent the offshore north. A clear offshore horizon cannot prove that a coastal plume is healthy. Nutrient management changes both quantity and balance, and plankton communities can respond to reductions in phosphorus and nitrogen in different ways. Long records reveal change, but not one uniform direction. Assessments under the Northeast Atlantic Marine Convention found complex trends among habitats and plankton groups in the Greater North Sea. In coastal and shelf waters, larvae of bottom-living invertebrates increased over the long assessment record, while some plankton that remained drifting throughout life declined. Phytoplankton biomass also changed across recent assessment periods. A bright bloom in 1 week cannot cancel a multi-decade trend, and a regional trend cannot predict every bay. Temperature now alters the same machinery. Warming can change stratification, metabolic rates, and the range of plankton communities. Its effect depends on the water mass and the nutrients available. Assessments under the Northeast Atlantic Marine Convention report different responses between southern nutrient-limited waters and northern waters influenced by Atlantic inflow. The useful conclusion is not that warmth simply makes more or less plankton. It changes the conditions under which different organisms succeed. Each observing method sees a different engine. Satellite color covers enormous areas, but is weighted toward the surface and interrupted by cloud. A plankton recorder samples a narrow path through water over many voyages. A bottle or net can reveal organisms and nutrients at one station, depth, and time. Long-term assessments combine these partial views. Apparent disagreement may reflect a difference in scale or method rather than an error in the sea. Biomass and production must also remain separate. Biomass is the living material measured at a moment. Production is the rate at which new material is made. A community can produce rapidly, while grazers remove cells almost as fast, leaving less visible accumulation than expected. A brilliant surface patch may contain abundant cells without describing what happened below it. The green engine is measured through rates, stocks, and communities, not color alone. Seen from orbit, the green engine looks like color. Seen through a net, it becomes organisms. Seen across seasons, it becomes timing. Most of what it produces is consumed, recycled, or lost before a bird or mammal can use it. Yet some of that dispersed energy is gathered into compact, moving bodies. They are small enough to hide inside a wave and numerous enough to reorganize the lives of predators. The next link is silver. From a distance, small fish can collapse into one flash of silver. The food web cannot afford that shortcut. Sand eels belong to a family of small burrowing fish, often called sand lances. Atlantic herring, European sprat, and Norway pout are different fishes with different life histories and distributions. All four are important forage groups in the Greater North Sea, but forage is a relationship, not an identity. It means that their bodies transfer energy to animals that eat them. The International Council for the Exploration of the Sea describes these four groups as major forage fish that feed predominantly on plankton and support the wider North Sea food web. They are taken by larger fish, seabirds, and marine mammals. All four also support fisheries, but they are assessed and managed separately. Their shared position creates a narrow-looking passage between many small producers below and many predators above. Ecologists sometimes call this a wasp waist structure. The metaphor needs restraint. The North Sea food web has alternative prey, changing diets and predators that feed at several levels. A decline in one forage fish does not produce the same response in every predator, nor does an increase guarantee that food is available where and when it is needed. The wasp waist is a way to notice the influence of a relatively small set of prey groups. It is not a claim that the entire ecosystem hangs from one species. Sand eels make the link unusually physical because much of their life is tied to sand. The North Sea name covers a group of species, with lesser sand eel the most abundant member in the regional complex. Their narrow bodies can disappear into suitable seabed sediment. That behavior joins the water column to particular banks and patches of coarse sand. A school seen feeding above the bottom may be connected to a resting place that the camera never sees. The lesser sand eel lays eggs on sand in winter. Larvae enter the plankton after hatching, commonly between February and April, and settle during May and June. After settlement, the fish form feeding schools in the water during daylight and bury in sand at night. Following the summer feeding period, they remain buried by day as well as night for much of the winter, apart from a short spawning period. The calendar varies, but the sequence explains why a survey can miss fish that are present. Suitable sand is not spread evenly. Evidence reviewed by the Scottish Government shows strong habitat preference, including an association with medium and coarse sand and avoidance of fine sediment in studied areas. Feeding schools usually remain near the banks used for burial, though measured daytime movements around Dogger Bank have varied between studies. Sand eels are therefore neither fixed in place nor freely mixed across the entire sea. That local attachment changes the meaning of abundance. A stock estimate can describe fish across a management area. A breeding bird experiences prey within a journey it can complete while keeping an egg warm or returning food to a chick. Fish may be plentiful beyond that range, buried during the wrong hours, too deep for a surface feeder, or the wrong size for the energy required. Availability is abundance filtered through place, time, and behavior. Predators apply different filters. A black-legged kittiwake takes prey near the surface and has limited diving ability. A puffin can pursue fish underwater and carry several crosswise in its bill. Guillemots and gannets use the water differently again. The Scottish Evidence Review therefore ranks species differently in their vulnerability to reduced sand eel availability. There is no scientifically honest category called the average seabird. Even a puffin returning with a full bill does not solve the identification problem. From the image alone, similar narrow prey may be difficult to separate. The bill can demonstrate successful foraging, transport, and scale without proving that every fish is a sandeel. If prey identity is not supplied by the photographer, field record, or a qualified review, the narration must stay general. A beautiful wildlife shot is not a taxonomic certificate. Size matters alongside identity. A chick may receive the same number of fish but less energy if the prey are smaller. A parent may compensate by making more trips, switching prey, or searching farther. But each option has a cost, and each bird species has different limits. Evidence from monitored North Sea colonies links breeding performance to sandeel abundance and availability, while also showing that weather, predation, diet flexibility, and colony location complicate the response. Herring gathers energy in another form. It is a clupeid rather than a sandeel, and it can form large pelagic schools. Sprat is also a clupeid, but it is not a young herring. Norway pout is a small gadoid related to cod rather than either of them. Their larvae, spawning places, movements, and fisheries differ. The silverlink is a guild assembled by ecological role, not one interchangeable body with 4 names. Those differences create resilience and competition at the same time. Predators may switch prey when one group is scarce, but the replacement may occur in a different place, season, or size range. Forage fish also consume overlapping parts of the plankton community and can affect one another through shared resources. A food web can absorb change without remaining unchanged. Flexibility buys time, but it does not make every loss harmless. Fisheries enter this passage because all 4 forage groups are commercially valuable. The International Council for the Exploration of the Sea lists separate North Sea fisheries for herring, sandeel, sprat, and Norway pout. The Scottish Evidence Review describes sandeel processed into fish meal and oil. The scale, season, and management of each fishery differ, as do the assessments behind annual advice. A vessel hauling small fish supports a named fishery only when its target, date, and location are known. Sandeel management is especially spatial. Evidence of limited movement and mixing led the International Council for the Exploration of the Sea to divide the North Sea complex into several assessment areas. Recruitment can vary sharply among years and places. A catch limit calculated for one area cannot describe the availability of fish beside every colony inside it. The unit needed for assessment, the patch experienced by a predator, and the boundary used by law are 3 different maps. 1 minute after midnight on 26 March 2024, a United Kingdom fishing license variation prohibited fishing for sandeel by all vessels within English waters of the International Council for the Exploration of the Sea Area 4, the North Sea. Every part of that sentence matters. The measure concerned sandeel fishing. It applied to English waters within a defined the International Council for the Exploration of the Sea Area. It did not, by itself, close every jurisdiction around the North Sea, and the official notice warned fishers that license variations can change. The closure was intended to protect an ecological resource as well as a fish stock, yet no boundary can command a strong year class to appear, keep plankton conditions favorable, or place prey at the surface beside every breeding colony. Management can remove one source of pressure and preserve options. Monitoring must then test what happens. A policy is an intervention in a changing system, not the final frame of a recovery story. This is also why the chapter cannot be built from anonymous underwater spectacle. A tropical bait ball, an Eastern Atlantic herring school, and a North Sea sand eel aggregation may all glitter, but they do not carry the same evidence. Where exact moving footage is unavailable, a labeled still survey map or restrained diagram is more honest. The film can explain absence. It cannot repair absence by renaming the wrong fish. Forage fish also act downward in the web. By consuming plankton, they influence the organisms below them while feeding predators above. The balance changes as fish grow, move, and switch prey. A strong year class can alter both competition and food supply, then fade as mortality removes it. This two-way influence is part of the wasp waste idea. It is another reason not to describe these fish as passive packets waiting to be eaten. Life stage further changes the picture. A drifting larva, a newly settled sand eel, and an adult feeding school occupy different parts of the system. Herring eggs, larvae, and adults do not share one distribution. Fisheries advice may concern a defined stock, while a predator selects fish of a particular size. Exact identification must therefore include age or life stage whenever the claim depends on it. The word fish is sometimes too broad, even within one species. When the link is present at the right place and time, its effect reaches the surface. A beak returns full. A porpoise changes direction beneath a tide line. A seal leaves a bank and moves into deeper water. Farther north, a dark back interrupts the horizon for a breath. These predators make productivity visible, but each follows a different map. To find their nurseries and hunting grounds, the sea must be read in seasons rather than borders. A nursery in the sea rarely looks like a nest. It is a place used disproportionately by a young life stage, often because food, temperature, depth, current or shelter improves the chance of survival. For some fish, an estuary or shallow sandbank performs that role. For others, the useful water moves or changes with season. Nursery maps are therefore species-specific evidence, not a promise that every small fish inside a shaded area belongs there. The camera can see sand, ripples, and turbid water without seeing a nursery. Juvenile fish may be too small, too dispersed or absent when the lens passes. Their use of habitat is established through repeated catches, age or size measurements, eggs and larvae, and patterns across surveys. A single unidentified fish above Dogger Bank proves only that a fish crossed the frame. The function of a nursery comes from evidence accumulated through time. One hunter is almost designed to escape a wide shot. The harbor porpoise is a small toothed cetacean with a low, brief surfacing motion. Beneath opaque North Sea water, it produces narrow band clicks and listens for returning echoes. The interval between clicks changes as it approaches prey. Passive acoustic instruments can record those sequences when no observer sees the animal. In this environment, sound is both a hunting sense and a way for researchers to detect hidden behavior. Protection for this mobile animal takes an unusual shape. The southern North Sea Special Area of Conservation stretches from north of Dogger Bank toward the Strait of Dover. It covers 36,951 square kilometers, from the low water line to depths of 75 meters, with most of the site shallower than 40 meters. Its boundary was not drawn around a reef or colony. It was built from observations and models of persistently higher porpoise density. The pattern changes with season. Approximately the northern two-thirds of the site is recognized for persistently higher densities in summer, while the southern part is more important in winter. In the management evidence, summer means April through September, and winter means October through March. These are assessment seasons, not migration gates. Porpoises can be present outside them, and the animal crossing a map line does not enter or leave the population. An often repeated estimate says the site supports 17.5% of the United Kingdom North Sea Management Unit population. The underlying document gives an essential caution. That estimate came from a survey conducted in July 2005 and is not a fixed count of animals living inside the site. Harbor porpoises move daily and seasonally, and those using the site belong to a wider population. The boundary protects recurring habitat use, not ownership of individual animals. Why porpoises gather in one water mass rather than another is closely tied to prey. But the site evidence is cautious. Depth, current, temperature structure, and seabed type can act as proxies for feeding opportunity when prey observations are incomplete. The conservation objective is therefore to maintain supporting habitats, processes, and prey availability. It does not declare that one sediment type mechanically creates porpoises. Food is urgent for an animal this small. Measurements from tagged wild harbor porpoises found high field metabolic rates consistent with frequent feeding. Other tag studies recorded intense attempts to capture small prey through day and night. The exact rates came from particular animals and places, so they should not become a universal North Sea total. The secure point is simpler. Losing access to feeding opportunities can matter quickly. Prey is not one species. The Joint Nature Conservation Committee advice lists gobies, sand eels, whiting, herring, and sprat among foods taken by harbour porpoise, while warning that diet within the protected sites is not well known. That uncertainty prevents a neat return to the previous chapter. A porpoise near a sandbank may be hunting sand eel. Without direct evidence, the film cannot say that it is. Predator footage shows behavior. Diet requires its own evidence. Tide can change opportunity at a scale smaller than the protected area. In a multi-year acoustic study at sites in the German Wadden Sea, season, time of day, and tidal phase influenced porpoise detections and feeding buzzes. The patterns differed strongly among recorder locations. That result does not create a universal rule for every porpoise. It shows that hunting behavior can be tuned to local water movement and local prey. Other cetaceans use a different North Sea. The International Council for the Exploration of the Sea places minke whales and white-beaked dolphins mainly in central and northern waters, while harbour porpoises range more widely. The European Small Cetacean Survey Series now holds 4 broad summer estimates for each of those species, from 1994 to 2022. Its trend tests, supplemented by 6 Norwegian estimates for minke whales, found no statistically supported change in North Sea abundance. Smaller real changes could escape detection, and the observed 2022 porpoise distribution was similar to 2016. Abundance, distribution, and certainty are different measurements. A minke whale surfacing in the north cannot stand for the southern protected site. A white-beaked dolphin filmed elsewhere in the Atlantic cannot prove North Sea behavior. These species may enter the chapter only through exact regional footage or language that names the material as illustrative. The rule is especially important for animals whose brief appearance already invites the audience to infer more than the camera recorded. Seals create another identification test. Grey seals and harbour seals share haul-out shorelines in parts of the North Sea, but they are separate species with different movements and regional histories. A crowded sandbank should not be called a seal colony until the animals are identified, nor should a haul-out be mistaken for their complete world. The same individuals may rest on land, travel through coastal water, and forage far offshore. Their status also diverges. The Northeast Atlantic Marine Convention's 2023 Integrated Assessment judged grey seal status good at Greater North Sea scale, while still reflecting recovery from earlier depletion. Harbour seals were not in good status because several assessment units failed abundance thresholds. Some areas increased over the long term, including the Wadden Sea. North Coast and Orkney, Shetland, and East Scotland did not achieve the long-term threshold. There is no honest basin-wide sentence saying simply that seals are recovering. Even those trends begin with a careful measurement. Monitoring programs count seals that are hauled out during defined survey windows, often around the moult. Not every animal is ashore and available to count. Methods and timing differ between species and countries, and results are assessed in geographic units. The count is an index interpreted through survey design. It is not a census of every seal swimming beyond the beach. The pressures overlap without becoming interchangeable. Fisheries can kill porpoises and seals through incidental capture or reduce prey. Impulsive and continuous underwater noise can disturb sensitive animals. Shipping adds sound and collision risk. Contaminants accumulate through food webs, while construction and climate alter habitat and prey. One stranded animal cannot prove which pressure acted, and one healthy surfacing cannot prove that the regional population is secure. Haul-out footage shows only one chapter of a seal's day. Land is used for rest, breeding, or molting according to species and season. Feeding happens at sea, often beyond sight of the beach. A tracking line can connect those worlds, but it belongs to the tagged animal and study period, not every seal in the colony. Behavior must be assembled from evidence without making one journey universal. A protected site also covers only part of a mobile animal's life. Porpoises can encounter nets, ships, and noise beyond its boundary, then return when prey or water conditions change. Management inside the site aims to preserve the qualities that make repeated use possible. Wider population status depends on pressures and habitat across a much larger range. The map matters precisely because it is limited. Hunters reveal the moving geometry of the sea. A porpoise follows sound and prey through a seasonal high-density area. A seal moves between a dry bank and an underwater feeding ground. A whale crosses the northern shelf without recognizing the line on a management map. Near the coast, the same tides expose mud and compress life against cliffs and islands. There, the North Sea's production leaves the water in wings. The most revealing moment on this coast is not always when a wave arrives. It is when the water leaves. A channel narrows. Sand and mud appear. Ripples hold a thin shine beneath the sky, and birds move into ground that was underwater only hours before. The sea has not vanished. It has changed its arrangement. At a tidal edge, the boundary between land and water becomes a schedule, exposing one habitat while covering another. Life has learned to work inside that repeated transformation. Along the coasts of the Netherlands, Germany, and Denmark, the Wadden Sea forms the largest unbroken system of intertidal sand and mud flats in the world. Its World Heritage property is not one feature. It contains tidal channels, shoals, seagrass meadows, mussel beds, sandbars, mudflats, salt marshes, estuaries, beaches, and dunes. Each lies at a different position between fresh water, salt water, and air. Together, they make a coast whose shape is maintained by movement rather than stillness. Every tide rearranges access. Water covers channels and carries animals across the flats. As it falls, buried and surface-living invertebrates become available to birds able to find them. Fish retreat with the draining water or remain in pools and creeks. a sandbank becomes a resting place. A high-tide roost may gather birds that fed far apart only hours earlier. The value of the system is not only how much food it can produce, it is how predictably that food appears, disappears, and appears again. From a distance, exposed mud can look almost empty. The birds prove otherwise. Bills of different lengths and shapes search different depths and surfaces. Some prey is taken in open water. Some lies within sediment. Some becomes reachable only when a particular stage of the tide slows or concentrates movement. This is a landscape of timing and partition, not a single feeding table. One flock may share the same flat, while its species use different parts of the hidden food beneath it. The numbers reveal a scale larger than the horizon. The United Nations Cultural Agency reports that up to 6.1 million birds can be present within the Wadden Sea World Heritage Property at the same time, while an average of 10 to 12 million pass through in a year. These figures belong to the protected property and its current assessment, not to every North Sea shore. Even with that boundary, the meaning extends far beyond it. Many of the birds are traveling between breeding and wintering grounds, separated by continents. A stopover is not empty time between the important parts of a journey. It is one of the important parts. A bird arriving after a long flight must feed, rest, and rebuild what the flight consumed. The quality of that pause can affect the next stage. The Wadden system therefore supports populations that spend much of their lives elsewhere. Its tide connects an Arctic breeding ground, a European coast, and a wintering area far to the south without any one bird needing to understand the whole map. Then the water returns. Feeding ground disappears beneath a reflective surface. Birds lift toward islands, salt marsh, sandbanks, or engineered high ground. The same change that closes one opportunity opens another for fish and marine predators. This is why a tidal flat cannot be judged from one visit. A high tide image and a low tide image may show the same coordinates while seeming to describe different worlds. The habitat is the full cycle, including the moments when its most visible surface is hidden. Farther west, the concentration moves upward. At Bempton, chalk cliffs rise above the North Sea and become a vertical breeding place. Gannets occupy ledges. Kittiwakes build at the cliff face. Guillemots gather shoulder to shoulder, while puffins use burrows and crevices. The details differ by species, but the shared solution is clear. A narrow edge of land gives access to open feeding water, while offering places where eggs and chicks can remain above the waves. These colonies look permanent when they are full, yet much of the spectacle is seasonal. Birds return, pair, lay, feed chicks, and depart on different schedules. A cliff filmed in early summer cannot represent the same colony in winter. Nor can one crowd stand for every species within it. Gannets, guillemots, puffins, and kittiwakes use the sea differently. Their nesting spaces, feeding depths, and travel ranges differ. The colony gathers those separate lives into one picture for only part of the year. On the Farne Islands, puffins return to land and nest below ground, while guillemots, razorbills, kittiwakes, terns, and shags fill other parts of the islands. Grey seals use the same archipelago on a different annual rhythm. The overlap is real, but it must not erase the calendar. A puffin-carrying fish is a breeding season image. A seal pup belongs to the autumn pupping period. Editing them together can show one place across time, provided the film says that time is passing. The return flight from sea to colony makes the food web visible. A bird arrives with prey. A chick calls. The adult leaves again. But the prey in one bill is not a basin-wide measurement, and its species should not be guessed from a distant image. What matters is availability as well as abundance. Fish may exist beyond a parent's efficient range, below the depth a surface feeder can reach, or at the wrong size and time for a growing chick. Presence in the sea does not guarantee delivery to the nest. This is why breeding productivity can change before a colony appears empty. Long-lived adults may return even when too few chicks survive to maintain future numbers. The Northeast Atlantic Marine Convention assessments examine abundance and productivity separately because they reveal different parts of the population story. Surface-feeding birds have been among the groups struggling in the greater North Sea, but the pattern is not identical for every feeder or location. A crowded ledge can be a powerful image and still be an incomplete measure of condition. The wider assessment is sobering. The Northeast Atlantic Marine Convention judged marine birds in the greater North Sea to be not in good status. That does not mean every species is falling everywhere. Some feeding groups and local populations perform differently, and the underlying data have their own spatial and temporal limits. The conclusion is regional and integrated. Its value lies in resisting the comfort of one successful colony. A nature film can celebrate a place without turning beauty into evidence that the whole system is secure. Food change is only part of the pressure. Climate can alter prey and the timing of seasonal events. Fisheries can remove or redistribute food. Disturbance can displace birds from feeding or resting space. Pollution, invasive predators, and disease can strike at different stages of life. Structures at sea may create collision or displacement risk for sensitive species. These mechanisms do not act equally on every bird. Their cumulative effect depends on behavior, route, season, and the geography of each development. That complexity changes how the crowded coast should be seen. The ledge is connected to a school of fish beyond sight. The mudflat is connected to a flyway crossing countries. A seal resting on sand is connected to feeding water outside the protected line. Conservation cannot stop at the visible gathering place. It has to follow animals into the spaces they use between gatherings, including routes that overlap with ships, fishing gear, platforms, and turbines. From the cliff top, that overlap begins to appear. Beyond the birds, a cargo ship moves along the horizon. A service vessel heads toward an offshore installation. Turbine towers form a pale line in the distance. None of these images cancels the wildlife in front of them. They reveal the modern North Sea as shared space. The question is no longer whether nature or industry belongs here. Both are already present. The question is how their pressures accumulate, how evidence is measured, and which users are allowed to change the others. At low tide, the working surface of the Wadden Sea can be seen. Offshore, most of the working sea remains hidden by distance. The next map must add what the horizon leaves out: fishing grounds, shipping lanes, ports, wells, platforms, cables, and pipelines. Beyond the colony, almost every direction leads into somebody's place of work. An empty horizon can be one of the North Sea's most misleading views. A trawler may be working below the curve of the Earth. A ship may be following a traffic route beyond sight. Under the surface, a pipeline can cross a cable beside a protected habitat. Farther offshore, a platform or turbine may stand outside the frame. Each use is real, yet no single camera position can show the whole arrangement. The apparent emptiness is created by distance, depth, and scale. To see the modern North Sea, the invisible layers have to be added back. Fishing was one of the first industries to make distance routine here. Archive film shows wooden vessels leaving harbor, men hauling nets by hand, and catches worked on open decks. That material belongs to a named year, fleet, and port. It cannot be used as though every method survived unchanged. Engines grew more powerful. Navigation became more precise. Gear changed. Cold storage and road networks altered where fish could be landed and sold. The sea remained a food source, but the machinery around each catch expanded. There is no single modern North Sea fishery. Some vessels tow nets through the water column. Others work close to or directly across the seabed. Pots, lines, seines, beam trawls, and otter trawls interact with different animals and habitats. Small coastal boats and large offshore vessels also support different patterns of employment and value. One rule can therefore affect fleets differently, just as one gear can affect habitats differently. The word fishing joins these activities for convenience. Ecologically, the gear, place, season, target species, and unwanted catch all matter. Management has changed the picture. Fishing pressure has fallen over recent decades. and the stock sizes of most groups of commercial species in the Greater North Sea are now, overall, above levels associated with maximum sustainable yield. That is genuine progress. It is not a declaration that every stock is healthy. Individual species can remain below reference levels, and commercial stock measures do not describe sensitive fish, bycatch, food web effects, or the condition of the seabed. The International Council for the Exploration of the Sea still identifies fishing as the main threat to ecosystem health across the ecoregion. Extraction removes target fish and can also kill animals that were never the intended catch. Bottom contact gear disturbs the floor with an intensity that varies sharply by location and habitat. In the latest ecosystem overview, the shallow depth zone was the most affected by bottom fishing pressure. Recovery can be slow, where sensitive seabed communities meet repeated disturbance, and faster when natural disturbance is already high. The lesson is not that one net explains every change. It is that reduced pressure and continuing pressure can be true at the same time. That tension reaches the key. A fish stock is an ecosystem component, a managed population, a catch limit, an income, and a meal, depending on who is looking. Coastal fleets can represent a modest share of total landed value, while remaining important to particular ports and families. Restrictions can protect future productivity and also change work immediately. A serious account has to hold both scales together. The people on deck are part of this sea, but human dependence cannot turn biological limits into opinion. Beyond the fishing grounds, merchant traffic draws another network. Tankers, container ships, bulk carriers, ferries, and service vessels converge on ports around the basin. Their routes are not random lines. Depth, separation schemes, hazards, schedules, and harbor approaches concentrate movement into corridors. A time-compressed traffic map can make the result look like a web of light. It must still be labeled as data, not filmed reality. Each point is a vessel report transformed into a picture of movement. Underwater, a ship announces itself differently. Propellers, engines, and onboard machinery add continuous sound to a sea already filled with wind, waves, and animals. The Northeast Atlantic Marine Convention's assessment found shipping noise dominant in the North Sea soundscape, especially in the south and along major routes. A vessel can leave the frame while its acoustic presence extends much farther through the water. The ecological thresholds and population effects are not all settled, so a noise map cannot become a diagnosis for every porpoise. It can show exposure, a human signal occupying the same water through which animals communicate, orient, and hunt. Ships carry more than cargo. Organisms can travel in ballast water or attach to hulls. Exhaust and other discharges create additional pressures, while dredging reshapes approaches needed to keep ports open. International rules have reduced some emissions and introductions, but risk has not disappeared. The International Council for the Exploration of the Sea attributes a majority of recorded non-indigenous species introductions in its Greater North Sea analysis to shipping. That percentage belongs to the analyzed records and period. It is not a count of every organism that has crossed the sea. At the coast, the separate networks become physical. A port is breakwater, channel, pilot boat, tug, crane, warehouse, rail line, and road. It joins an offshore movement to land-based labor and consumption. Sediment must sometimes be removed from navigation channels. Ships refuel, unload, and wait. Fishing catch, energy equipment, and ordinary goods can pass through neighboring berths. The harbor is not where the working sea ends. It is where hidden routes become visible as schedules, machinery, and people. In 1969, a discovery in the southern Norwegian North Sea opened another industrial scale. Ekofisk began test production in 1971 and ordinary production in 1972, in water only about 70 meters deep. That combination matters. Hydrocarbons lay kilometers below the seabed, but the working structures stood in a shelf sea. Platforms, wells, processing equipment, accommodation, and supply vessels created a settlement with no streets, connected to coasts it could not see. Ekofisk did not remain one isolated platform. The field was redeveloped with many facilities and linked to other fields and export systems. Oil now travels through an export pipeline to Teesside in Britain, while gas travels to Emden in Germany. The useful product disappears beneath the surface long before it reaches land. That is the recurring visual problem of the working sea. The most important connection may be a line on a chart, a valve on the seabed, or a flow inside a pipe. Across the Greater North Sea, offshore oil and gas has brought physical structures, pipelines, drilling, seismic sound, atmospheric emissions, and controlled or accidental releases. Regulation and industry measures have reduced several emissions and discharges since earlier assessments. Those reductions matter because they show that an industrial footprint is not fixed. The infrastructure itself still occupies habitat and eventually reaches the end of its working life. Progress in one pressure does not erase the others, nor does a list of pressures show that every installation creates the same effect in every place. The human cost of offshore work entered public memory on the 6th of July, 1988. A series of explosions destroyed the Piper Alpha platform, and 167 people were killed. The number should not be accompanied by a spectacle assembled from unrelated fire. It represents workers, families, survivors, and a disaster examined in a public inquiry. In this film, the sea and the platform can remain quiet, while the date and loss are stated without embellishment. Lord Cullen's inquiry did more than reconstruct a night. Its consequences helped reshape the United Kingdom's offshore safety regime. The safety case approach requires the duty holder to identify major hazards and demonstrate how risks are controlled, while goal-setting law places responsibility on operators to meet safety objectives rather than merely follow a fixed list. No regime can make hazardous work free of risk. The lasting change is that safety must be argued, evidenced, reviewed, and updated as an installation changes. An offshore structure also has an afterlife. Wells must be made secure, equipment may be removed, steel and concrete must be assessed, pipelines considered, waste brought ashore, and sites monitored. Under the Northeast Atlantic Marine Convention framework, leaving a disused installation at sea is generally prohibited, with defined categories and assessment procedures for possible exceptions. Decommissioning is therefore not the simple reverse of construction. It is another long project imposed on the same weather, seabed, and network of vessels. Now place every layer on one map. Fishing intensity crosses shipping density. Port approaches meet dredged channels. Oil and gas fields connect through wells and pipelines. Telecommunications and power cables occupy routes on the floor. Protected habitats overlap the spaces between them. The image becomes crowded, but even this is incomplete. Datasets come from different years, resolutions, and definitions. Some pressures travel beyond the footprint that created them, while other overlaps on a map may never occur at the same moment. A cumulative map is not a verdict. It is a warning against judging any new project as though it enters an unused sea. The oldest industrial layers are now meeting the newest. Service ports that once faced oil and gas increasingly handle turbine foundations, blades, cable, and installation vessels. Some skills and routes can be reused. Other infrastructure must be removed or repurposed through separate decisions. Out on Dogger Bank, the former high ground in this story is becoming an electrical landscape. The working sea is not being replaced by a green sea. Another immense use is being added to all the uses already there. From the deck of an installation vessel, a turbine does not look like a clean symbol on a horizon. It arrives in pieces. A tower section fills the frame. A blade passes overhead like a bridge being lifted through the air. Below the waterline, steel continues into sand. Around it move cranes, cable ships, survey vessels, and crews. The finished rotor may appear effortless. The landscape that makes it turn is anything but. This construction is taking place on Dogger Bank, the shallow plateau that has returned throughout this story. It was once part of a wider inhabited landscape. Later, it became fishing ground, habitat, charted hazard, and protected seabed. Now, part of the bank also carries an electrical network. The ground has not changed its name. Its role in human life has changed again. The development is divided into Dogger Bank A, B, and C. Each phase has an installed generation capacity of 1.2 gigawatts. A and B are each designed around 95 13-megawatt turbines, about 131 kilometers from shore at their nearest points. C is farther out, about 196 kilometers from shore, with 87 14-megawatt turbines. Together, the design totals 277 turbines and 3.6 gigawatts. That design is not the same as completion. On the 16th of July, 2026, the developer reported that commissioning continued on Dogger Bank A. At B, 30 turbines had been installed. Notices for C during June and July listed inter-array cable installation, cable burial, and scour protection work. This is a dated construction record, not a permanent description. By the time these words are heard, the numbers may have moved. Before a blade can turn, the seabed must carry it. Each turbine stands on a monopile joined to a transition piece above. In November 2025, the project announced that all 277 monopiles and all 277 transition pieces had been installed across the 3 phases. Completion of the foundations did not complete the wind farm. Towers, turbines, cables, protection, testing, and commissioning still had to follow in different places. The machines are connected below the surface. Inter-array cables gather electricity from turbine to turbine and carry it toward a converter platform. Export cables then carry power toward land. On Dogger Bank A alone, the project reported more than 328 kilometers of inter-array cable installed by July 2024. Routes are cleared, trenched, laid, buried, and later surveyed. The quiet line on a diagram is a long construction site on the seabed. Distance changes the electrical system. Each phase has an offshore converter platform. The turbines produce alternating current. The platform converts it to high-voltage direct current for the long journey ashore, where another converter returns it to the grid. A and B connect through East Riding of Yorkshire. C connects through Teesside. The Forest of Towers is therefore only the visible part of a chain reaching through buried cable, substations, and inland transmission. .6 gigawatts is nameplate capacity, the maximum combined output stated for the installed machines, not a promise of continuous generation. Wind varies. Turbines stop for maintenance, constraints, or weather beyond their operating range. Supply and demand must still be balanced across a larger electricity system. Capacity describes the size of the equipment. Energy describes what it produces through time. Confusing the two can turn an engineering number into a claim it was never meant to make. The developer estimates that the completed project could generate over a year electricity equivalent to the annual use of about 5.85 million medium-use British homes. That comparison assumes a projected 55% wind load factor, a household figure of 2,700 kilowatt-hours, and estimated transmission losses. It does not mean 6 million named homes receive a private supply, or that the farm produces its maximum output every hour. Why build at this scale? While a turbine is turning, it produces electricity without burning coal, oil, or gas. A power system with more low-carbon generation can reduce the fuel combustion that is heating the ocean and raising sea level. Offshore wind is therefore part of the United Kingdom's plan to decarbonize electricity. But a turbine is not made from wind. Steel, concrete, cables, vessels, ports and grids all have material and energy costs. Climate benefit does not erase local consequence. It changes the question. The relevant comparison is not between an industrial wind farm and an untouched imaginary sea. It is between real energy systems, each with effects in different places and times. Reducing greenhouse gas emissions addresses a global pressure. It does not grant permission to ignore a porpoise near a pile driver, a bird crossing a rotor field, or a community whose fishing ground has acquired new obstacles. Foundation installation can introduce intense impulsive sound underwater. Harbor porpoises rely on sound to navigate and feed. Mitigation can reduce the risk of injury, yet disturbance may still move animals away from an area during noisy work. The Joint Nature Conservation Committee's cumulative modeling for Eastern English waters states the central uncertainty plainly. The wider population consequences of that disturbance remain unclear. A detected response and a population-level effect are not the same measurement. Birds meet the development differently. Some species avoid turbines or lose access to feeding space. Some cross rotor height and carry collision risk. Others show weaker responses or may be attracted to structures. Assessments under the Northeast Atlantic Marine Convention report observed displacement and collision risk, while warning that cumulative population effects of expanding offshore renewables have not yet been adequately assessed. There is no honest result called the effect on seabirds. Species, season, route, and behavior all matter. At the bottom, a monopile occupies a small point but changes the ground around it. Preparation, scour, and protective rock can replace soft sediment with hard surface. Cable trenches and anchors disturb wider strips before burial and recovery. New structures can be colonized, creating local habitat while changing the community that belonged to sand. None of those outcomes is captured by saying that the seabed is either destroyed or improved. The answer depends on what was there, what replaced it, and how long the change lasts. Power cables add another set of questions. Regulators require assessment of burial, electromagnetic fields, repair disturbance, and the consequences of scour protection. Different animals sense and use the seabed in different ways, and evidence does not support one universal response. The correct image is not a glowing force field beneath every cable. It is a surveyed route, a set of testable mechanisms and uncertainty that can be reduced only by measurements made before and after construction. The new geometry also intersects work already underway. Construction zones, moving vessels, and buried cables affect navigation and some kinds of fishing. Trawling may be constrained where potting can remain possible depending on safety, agreements, and the site. Current Dogger Bank notices publish vessel activity and fisheries contacts because coexistence is not achieved by drawing two uses on the same map. It is negotiated through routes, timing, gear, communication, and evidence of what actually changes. Monitoring is how predictions meet the sea. Hydrophones can record porpoise clicks and construction noise. Aerial surveys can count birds while accounting for effort and detectability. Cameras and grabs can revisit sediment and animals around foundations. Cable surveys can test burial and exposure. Fishing records and vessel tracks can reveal displacement, though neither explains motive by itself. Every method sees only part of the system, and a short record can miss a slow population response. Evidence should change practice. It can alter the timing of noisy work, the method used to install a foundation, cable protection, vessel routes, monitoring effort, or the location of future development. It can also show that a feared effect is smaller than predicted. Adaptive management requires both possibilities. Monitoring that can only confirm a prior decision is not learning. Uncertainty is not a reason to measure nothing, and a mitigation plan is not proof that an impact has disappeared. The contradiction cannot be edited away. The North Sea needs lower carbon energy, and the North Sea is already under cumulative pressure. Both statements can be true. The task is to reduce the global damage of energy while measuring, avoiding, and repairing local damage as rigorously as possible. On Dogger Bank, a landscape once crossed on foot is becoming infrastructure for a changing climate. Beneath it, sand, fish, birds, and mammals continue to move through the same space. Steel can be fixed to a coordinate. A cable can be charted. A turbine can be counted and commissioned. The water around them offers no such stillness. Its temperature, chemistry, and living communities are already shifting across the very bank these structures were built to serve. The final change in this story is not another object placed in the sea. It is the sea itself moving again. The change is visible in a record, not in the color of one wave. The European Environment Agency reports that North Sea surface temperature rose by about 0.3 degrees Celsius per decade from 1991 to 2024. That is an average across a defined sea and period, containing warm years, cooler years, and local differences. It cannot identify the cause of one stranded animal or one storm. Weather remains noisy inside climate. Winds change direction, cold snaps occur, and natural cycles redistribute heat. Climate change alters the background on which those events unfold. Event attribution asks whether human influence changed probability or intensity. It does not begin with dramatic footage. A warming trend is established by repeated measurement, not by selecting the hottest-looking water. Much of the North Sea is shallow, but it does not respond uniformly. Tides keep southern water mixed, while deeper northern water can stratify by season. Atlantic inflow, rivers, cloud, and wind alter local conditions. The Northeast Atlantic Marine Convention finds different biological responses across the basin. Warming does not slide every species north together. It changes habitat through depth, food, oxygen, timing, and competition. At the base of the food web, the response is more complex than more or less plankton. Across Greater North Sea, records from 1960 to 2019, the Northeast Atlantic Marine Convention linked rising temperature with increasing meroplankton and decreasing copepods. Other trends differed by habitat and nutrients. Meroplankton are temporary drifting stages of bottom-living animals. Many copepods remain planktonic throughout life. Their changing balance can alter what food is available and when. Timing moves with distribution. The International Council for the Exploration of the Sea reports that the seasonal cycle of some North Sea zooplankton has advanced by 4 to 5 weeks with higher temperatures. That does not move every bloom 1 month earlier. It is a measured shift for particular organisms. Predators may adjust at a different rate. Food can remain abundant and still arrive outside the narrow period when larvae or chicks need it most. Fish do not simply march toward the pole. During warming of 1.6 degrees between 1980 and 2004, the North Sea demersal assemblage deepened by about 3.6 meters per decade. Latitude changes were mixed. Widespread temperature specialists shifted north on average, while some small southerly species with limited North Sea ranges shifted south. Depth and latitude tell different parts of the change. For fisheries, moving distributions become a management problem. Surveys, ports, quotas, and agreements were built around geography that may not remain stable. English planning for North Sea and Eastern Channel flatfish expects temperature and salinity change to alter habitat suitability, while acknowledging uncertainty. Adaptation means updating management with research, not pretending tomorrow's catch can be read from today's map. At a seabird colony, climate often arrives through food. Warmer water can alter plankton, then the recruitment, timing, and location of forage fish. Surface feeders may not reach prey that moves deeper or farther away. The Northeast Atlantic Marine Convention links some North Sea prey and breeding changes to rising temperature, but also identifies fishing, disease, and disturbance. One failed nest cannot identify its cause. Long records reveal the pattern. Marine mammals add another moving layer. The International Council for the Exploration of the Sea reports that harbor porpoise distribution shifted south with changing prey availability, while other cetaceans show different patterns. Climate may act through food and habitat, but bycatch, contaminants, noise, and shipping remain pressures. A sighting beyond a familiar range is not, by itself, evidence that a population grew or that temperature was the only driver. The coast records change in another unit. The Met Office reports that mean sea level around the United Kingdom has risen about 20.1 centimeters since 1901, with a likely range from 16.6 to 23.6. About 2/3 occurred during the last 3 decades. This is a United Kingdom coastal index, not a measurement for every North Sea harbor. A higher mean level raises the starting point for tide, wave, and surge. It does not make every future storm stronger. United Kingdom climate projections identify sea level rise as the main mechanism expected to increase coastal flood risk, while changes in storm surge severity remain smaller and more uncertain. Centimeters added quietly between storms can matter when wind pushes water toward land. No instrument can follow all of this. Satellites measure the surface. Ships lower sensors through depth. Plankton recorders and fisheries surveys repeat routes. Hydrophones listen when mammals are unseen. Colony counts track birds, and tide gauges hold the coast against time. Their strength comes from repetition and calibration. One observation can reveal a question. A long series can show change. Management must move with evidence. Fishing rules can respond to recruitment and shifting distributions. Protected areas can reduce pressure at important places, while mobile animals also need routes and food beyond fixed boundaries. Offshore construction can change method or timing when monitoring finds risk. Coastal plans can use rising thresholds. Adaptation is not one final decision. It is a promise to measure again and respond. Restoration can give the coast more ways to respond. Salt marsh and mudflat can dampen wave and tidal energy before it reaches defenses. Tidal exchange, oyster reef, seagrass, and marsh projects can reconnect coastal habitat. These are local interventions, not substitutes for cutting emissions. Their performance must be monitored, and space must remain for habitats to move as water rises. In the Wadden Sea, 3 countries frame adaptation around natural dynamics, interconnection, flexibility, long time scales, and site-specific decisions. Its assessment calls for stronger observations and closer movement of evidence into management. That is an honest response to a coast that cannot be frozen. Protecting people and allowing a living shore to adjust are not simple companions, but neither can be planned from one snapshot. Doggerland returns as evidence, not prophecy. After the last ice age, sea level rose across a landscape already altered by rivers, sediment, and people. The modern crisis has a different cause and society around it. The same map will not repeat, but a coastline is an agreement among water, land, and time. What seems fixed within one lifetime can move in a longer record. The North Sea is dangerous, not because it is exceptionally deep, but because shallow water joins atmosphere, seabed, and coast tightly. Tides stir nutrients, while storm waves interact with the shelf and opposing currents. One bank can hold sand dunes and foundations. One tidal edge can shelter millions of birds and expose towns to surge. Productivity, danger, and human use are consequences of the same connection. At last, the structures fall behind. No storm is required. In fading light, a real North Sea horizon carries small waves toward shore. The water is neither empty nor settled. Lives continue in sand, current, and cold. Beyond the frame, instruments keep measuring. The sea moves, as it always has. What changes now is the speed. the pressure, and the care with which we watch.